Ladies and gentlemen, once again, you are welcome. In our last lecture, and you can always ask questions by typing your questions there. In the last lecture, we were able to look at this model on your screen. We solved for the variables. We formulated the model in a non-standard form. And now in the standard form. The standard form is what you see on your screen up here. We're able to do that. We were able to find the optimal solution for fan yogurt and fan choco. We identified the slacks. We found the Z variable, the profits of the company at the optimal. Okay, and we're able to see that at the optimal level, that gave us a profit of 1360. There were 0 slacks for both the milk and the labor constraint. Now, this is not to say that at the optimal, you must always have 0 slacks. Okay, sometimes you have 0, sometimes one of the slacks or some of the slacks will not be 0. So today, this is how we ended last time. We ended at this function where we had formulated a non-standard form. And I presume that how we got this particular value, you can go to our next video. Please remember to subscribe to the video so that you can get a quick notification the moment I upload it. Today, we want to start with a minimization. Remember the last time we dealt with maximization. So we want to start with a minimization problem. Now, because I've already told you that it's a minimization, it's like you give you the answer as to what kind of parameter, what kind of objective we are going to deal with. You automatically know that it's going to be a minimization. But under the circumstances, there must be something in the storyline that will tell you that it's a minimization or it's a maximization. And the best way to start this is by understanding. The most important thing in a linear programming problem is understanding the model. So I want somebody to do the reading for me, and then we'll begin to look at the entire formulation, because once you crack the formulation, you are good to go. Who's going to do the reading for us? Okay. Who will try to do the reading for us? Amana, please start.
Okpo wants to plant maize this month and needs to fertilize the field. He can fertilize with NPK brand or urea. Each brand yields specific amounts of nitrogen and phosphate per bag as chemical contributions. Brand nitrogen 1 B per bag, phosphate 1 B per bag. NPK nitrogen 2, phosphate 4. Urea nitrogen 4, phosphate 3. Okpo's field requires at least 16 pounds of nitrogen and 24 pounds of phosphate. NPK costs 6 Ghana cedis per bag. Urea costs 3 Ghana cedis per bag. The farmer wants to know how many bags of each brand to purchase to minimize total cost of fertilizer given the data above. Identify the DVs and formulate an LPP. Find the optimal solution graphically.
Thank you. So DVs are the decision variables. And then you have the known as the linear programming problem. Now, when you look at this, I told you, you can see from the situation that here, it's a clear indication that you are minimizing total. So you will see something, even if he has not mentioned minimize total cost, okay, by talking about total cost, you know that we are going to minimize. All right, my first question I want to ask you is, looking at this storyline, the first thing to identify actually is to identify the decision variables. So what are the decision variables? Who can tell us what are the decision variables? What are the decision variables? Amana.
So the decision variables would be NPK brand. It would be nitrogen and phosphate. Sorry.
Okay. So that was a very tempting, and it's deliberately designed to tempt you to think that the decision variables are nitrogen and phosphate. But let me always give you, and I've done this before, let me give you a way to identify the decision variable. I told you the other time, and I'm going to use this principle that I used the other time to share something with you. I told you that one of the things for you to know about the decision variable is that it is the one that carries the costs or that carries the benefits associated with the storyline. Okay, so you have the costs or the benefits that are associated, with the storyline. So if you have a particular, cost, you have to look for the storyline and identify which one has a cost or a benefit associated with it. So looking at this, the items you mentioned nitrogen, phosphate, you mentioned NPK, urea. Which one of them has got some costs or some revenues or some profits or some distance traveled or some audiences and things like that? Which one have got that associated with it?
I think is the nitrogen and urea.
It's not a nitrogen and urea. It's not a nitrogen. Yes, unisophosyne.
The NPK and urea.
NPK and urea. Okay. These ones are the ones that have got costs associated with them. Okay. They are the ones that have got costs associated with them. Now, it means that you don't have to rush to think that something is the decision variables. Okay. You don't have to rush, because once you rush in, you will rush out. You might think that you have the answer to that, but that is not the case. So, and you can see that, you got to know what is our focus on. What are we going to decide on? He can fertilize with NPK brand or urea. Okay, he can fertilize with that. Of course, that doesn't give you anything. Then you are told that each brand will yield specific amounts of nitrogen and phosphate per bag. Then so of course, that one too will not give you a clear, information. But this is where you get a clear information. You were told that Ogbo's fields requires 16 pounds of nitrogen, requires that. If you require at least 16 pounds of nitrogen, that should tell you that it is going to deal with something that is more or less like a resource. It is that sort of a resource needed because the field requires that resource. But the most important one is that knowing very well you're going to minimize cost, you should know the things that are going to incur cost. The things that are going to incur cost. And from the story, NPK is going to incur a cost of 6 Ghana cedis per bag. Urea is going to incur a cost of 3 cedis per bag. So that will give you the clue that it's not just a minimization, but it's a cost minimization. And this cost minimization requires some amount of. So how will you now formulate your decision variable? You will say let, and don't forget the unit of measurement. You will say let x1 be equal to blah, blah, blah. Let x2 be equal to blah, blah, blah. Let x3 be equal to blah, blah, blah. That's also, okay, depending on how many decision variables you think are there. So who can tell me how we should call let x what be what? Who can formulate that for me? Yes, who can formulate that? Let what be what? let X1 be equal to what? Janet. Janet.
Yes, sir. So since NPK is the first one, we'd say let S1 be NPK and S2 represent urea.
Okay, you remember that I always tell you that don't just say let X1 be fine, you go, let X2 be fine choco. Okay. I indicated clearly that you should always bring the unit of measurement attached.
So
you are now correcting it, isn't it?
yes, but then the slide is gone.
Yes, because you didn't look at it. So I don't want you to correct it because I just told you. I'm only telling you the correction because you are wrong.
Okay, sir.
And you will know. Because by me telling you that you should do it, of course, you're going to do the correct one. So next time, note it. And I indicated I should note it ahead of time. Okay. So let me show you the slides and then you tell me. So how will you formulate it? Let's go to, yes, Eunice. Stephen Morrison.
Hello, Doc. Please let X1 be the number of bags of NPK.
Continue.
Then let X2 also be the number of bags for urea.
Okay. Thank you. So that is how it's okay. So X1 will be bags of NPK. Okay, that will be X1. So if you are writing your decision variables, okay, let's do that here. If you're writing it, you say let X1 be bags of NPK. And then X2 be equal to number of bags or bags of urea. So now, and always master this, the first thing to do is to define your decision variables. That is the very first thing to do. You want to define the decision variables. If there is X3, you will know. If there is X4, you will know. Okay. It is from this that you now go to the next step of formulating your objective function. So how are we going to formulate this objective function? We'll represent it as what? Who can tell us? Knowing from previously, how would we formulate the objective function? How would we go? Don't tell me the values, but the first thing that will come, Amana.
Sir, we are going to do it. Z is equal to C1x1 plus C2x2. And the Z is going to be minimum.
All right. However, we want the actual values now. We want the actual values now. So now let's go to the storyline and then you tell me how we are going to properly do the minimization. Who can raise their hand and tell me how we are going to properly do the minimization? Okay, maybe I need to show you the storyline. How will we do the minimization? How will you do the objective function formulation? Looking at the content, because that C1 and that C2 are numbers that will always be given to you. And you have to know them. So how will you proper, Michael?
Yeah, Doc, I want to give that a try. So it will be Z minimize. Let's see.
Yes.
Z mini equals 6, which is for the number of bags for the NPK.
So I'll write it as well. Just say it and I'll write it.
6x1 plus the bags for the cost for the urea, which is the 3x2.
Okay, 3x2. That is perfectly fine. So that is that is exactly the objective function. Okay, that is exactly the way you formulate the objective function. It is the most important thing because once something is wrong here, forget it. Everything is dashed away. The ability to master and formulate the objective function is the first super challenge that you got to overcome. Okay. After this, you bring a certain word or phrase before you move on to the next one. What is a word or phrase? What is that word or phrase? Amana.
Subject to constraint.
Okay, so you bring the subject to constraint. Okay, so now you're going to formulate a constraint. Okay, so let me go to the next page and I'll show you something. So now I'm just going to write at the top here, you have z min, okay, equal to 6x1 plus 3x2, subject to. Now, what will be the name of the first constraint? Okay. Looking at the storyline, what will be the name of the first constraint? I just want a name, and then the name of the second constraint. It will be called what constraint? What constraint? Eunice. Eunice, what's the name of the first constraint? Michael.
The nitrogen.
And the second? Oxygen, what do you call it? Nitrogen is the first one, phosphate is the second one. So those are the constraints. Okay. So who can formulate the nitrogen constraints? I'm going to go there and then you formulate the nitrogen constraint. It's a very, very simple thing. So nitrogen constraint. Nitrogen constraint, who is going to tackle that for us? Nitrogen, Michael.
Doc, it will be, please, if you could move to the, I want to use the figures. If you could move to the other slide.
I wanted you to actually look at the figures before we go there.
I know it's 4 and 2, but I don't know which one precedes.
Okay, you have them.
Okay, so it will be 2x1 plus 4x2.
Okay. What about the phosphate constraint?
So 4x, that one will be 4x1 plus 3x2.
Good. All right. Okay, let's write that. Of course, there are other things that are involved, but let's write that first. So this is the nitrogen constraint and this is a phosphate constraint. Okay. So this will be, it should follow the same line. So it should be 2x1 plus 4x2. Okay, 2x1 plus 4x2. And then the next one will be 4. X1 plus 4x1 plus 3x2. 4x1 plus 3x2. Now, we indicated that these ones represent always, they represent the usage. The usage. Okay, if you can remember, we indicated that they always represent the usage. So that's the usage here. Okay, that's the usage. Okay, the usage. And then we indicated that you need a sign and finally another word, which we called available in the maximization. But this is a minimization. Okay, so we will not call it available, but we'll call it resource requirement. Okay, resource requirement. And you'll come to understand that very soon. So let's understand the resource requirement and before we even bring out a sign, let's understand the resource requirement for each one of these nitrogen and phosphate. So look at the storyline. Okay. The storyline will guide you. It says that Ogbo's field requires, that's a resource. It requires at least 16 pounds of nitrogen and 24 pounds of phosphate. Okay. So what is a resource requirement for nitrogen and what is a resource requirement for phosphate? It's very simple. The resource requirement, and I'm going to use the same thing to indicate what we have been dealing with. The resource requirement, okay, we're talking about those two. One is 16 and the other is 24. So you have 16 resource requirement, and then you have 24. Okay. Now, what is the unit of measurement? Well, it says pounds. Okay. So you can talk about pounds of nitrogen. Pounds. I just want to. Okay, 16 pounds of nitrogen, 24 pounds of that. Now remember, that is what is required to be able, but that is not what was actually used. So we need to know a symbol, but the symbol situation was given to us. And the symbol situation was given to us as, it said it requires 16, at least 16, at least 16. What symbol, ladies and gentlemen, what symbol is at least 16? What symbol is that, Stephen?
So greater than or equal to, please.
Good, greater than or equal to. This one is either you know or you don't know, okay? And it is greater than or equal to. At most, it's less than or equal to, okay? So you have a symbol of at least here, and therefore you just bring that to be greater than or equal to, greater than or equal to, because both of them have at least. Now, with this principle, if you don't take it, you will not understand the story. There's one more constraint that is left, don't forget it. It's known as the non-negativity constraint. Non-negativity. Now, that is x1, x2 greater. Now, ladies and gentlemen, I wanted to go back now to understand this principle of the resource requirement. So you need a certain resource, but you see, there is a minimum resource requirement that was given. So if I can even add the word minimum here. So the resource requirement is minimum. Now, how is that reasonable? It's reasonable because sometimes the doctor will tell you that the minimum number of sugar cubes to take, the minimum number of sugar cubes to take is this. So you have a minimum number of items to deal with. Minimum. So how do you deal with that? So what it means is that you can have more than 16 of the nitrogen, the pounds of nitrogen. You can have more, you can have 18, you can have 20, you can have 100, but you cannot have below 18. The minimum number of nitrogen you can have. Remember, you need 2 of the nitrogen, sorry, you need nitrogen to be able to produce, to be able to get one particular, NPK, you need a certain number of nitrogen and a certain number of phosphate. And the same way, a certain pounds of nitrogen, okay, is needed to produce NPK and urea. So X1 is NPK, and then you have urea here. A certain number will indicate that. So how do you now deal with this very situation of resource requirement? So always remember that it's not all the time you have what is available, but rather you have the minimum that you need. Understand that and note that down. You have a minimum you need. It's not always what is available, but also the minimum of what you need. Michael is asking, so Doc, in a constraint where word exact is used, the sign will be equal to yes. Okay. If it was, the storyline had been Ogbo's fields requires exactly 16 pounds, then you need equal to. If it had been Ogbo's field requires at most 16 pounds, then you need less than or equal to. Okay. If you have had things that Ogbo's field needed no more, okay, no, better still, no more than 16 pounds, no more than 16 pounds, okay, that is less or equal to 16 pounds. If it is no less than 16 pounds, which is what we have here, no less than 16 pounds, then it becomes at least 16 pounds. These terminologies, these words are very, very important. I'll take my time later on to walk it through there because English and mathematics move in certain differently. The opposite of less than is not mathematically speaking greater than. But then the opposite of less than is mathematically speaking is greater or equal to. Mathematically speaking, not English speaking. And so it's very important to understand those particular terminologies. So we need no less than 16 pounds of nitrogen and 24 pounds of phosphate to be able to handle the situation. Okay, so once you've been able to do this, now let me show you the formulation. Okay, this is your formulation. This is your formulation, and you have these constraints indicated there. You have all of these constraints indicated there, and of course your non-negative constraints. So now we are about to now construct our model. We're going to solve it right here, right now. We're going to solve this. So how do we solve it? Well, the first thing to do is to write our non-negativity constraint. So let's go and draw our non-negativity constraint. We're going to use the graphical approach as always. Okay. Non-negativity constraint. So bring your x1 here and then the x2 there. And the first thing is the non-negativity constraint. So what I just did is the non-negativity constraint, nothing more. Now, let's go to our nitrogen constraint. It's 2x1, 4x2. Okay, it's 2x1. And we are going to use equal to know the limit, the boundary. So you have 2. You have 2x1 plus 4x2 equal to 16. You assume that if x2 is 0, what is x1? And actually, if x2 is 0, then x1 will be equal to what? Who can tell me quickly? Okay. If x2 is 0, what is x1, Mark?
8.
Please 4.
8, let's go. Okay, so that's 8. Now, if x1 is 0, what is x2? Mark?
4.
4. So we have x1 being 8. So you look on the axis there at the bottom, x1 is 8. So you identify some 8 there, then you write 8. And then x2 is what? 4. So you identify 4 somewhere here, and then you write your 4. Now you join the 2 together, okay, and that gives you a beautiful line. And this line is a nitrogen line. So let's give it nitrogen constraint line. Okay. Now let's do the same thing for the phosphate. Okay, the phosphate. The equation is 4x1 plus 3x2. Okay, so use a different situation to look at this. Okay, so you have 4x1 plus 3x2 equal to, and the number that was there was 24. Equal to 24. Oops. To 24. Now, if x1 is 0, what is x2? I want to go quickly. If x1 is 0, what is x2? Janet. If x1 is 0, what is
X2 is 8.
sorry?
X2 is 8.
Okay, x2 is 8. If x2 is 0, what is x1?
6.
6. So you have x1 being 6, which is somewhere there, and you have x2 being 8, which is surely going to be above the 4. Okay. Then you join the 2, and then you have something like this. And this is actually phosphate constraint. Phosphate constraint. Phosphate. Now, you can see that we have these two constraints. And remember the symbol. Let me just take you back to our equation. Okay. The equation says that whatever is inside the feasible solution area is supposed to be greater than this 16. The limit, it should be greater. So when you look at this space that we have drawn, is if you look at a 16, which is this line here, is a limiting 16 for the nitrogen. And this line, this orange line, is a limiting 24 for the phosphate. And we want the space, we want to show the feasible solution area, and which is what is used, okay, the usage. The usage should be greater than these minimums. So the spaces we are looking for, are they going to be inside these lines, below these lines, or above the lines? You can tell me. The spaces we are looking for, are they going to be below the lines or above? Kajita?
I think they will be above the line.
They'll be above the line, okay? So the area you are looking to shade is going to be an area like this, okay? These areas, these areas, these areas, these areas. So we're looking at area from this section up to that section, okay? We are shading all of that. This is the area in question. And of course, it also includes the line. Amanda, do you have a question? It also includes the line.
Sir, please, can you please just go over what you just said?
Okay, so what I said is that the feasible solution area should be a space in the entire production possibility set that we have here. And the symbol, the equation, has a symbol which is greater than or equal to. And now, what should be greater than or equal to? The greater than or equal to is referring to 2x1 plus 4x2, which is the usage. The usage. It should be greater or equal to 16 pounds of nitrogen. The amount of nitrogen that is used should be greater or equal to the minimum requirement of nitrogen that is supposed to be. The minimum requirement is 16. So whatever we want should be above 16, whatever we are using, which is a 2x plus 4x, 2x1 plus 4x2. Whatever we are using is supposed to be greater than or equal to 16. Now, what is 16? 16 is the minimum. The line that we drew, this red line, okay, 4, 8, red line, is a 16. And then the 8, 6 line, 8, 6 line is the 24 phosphate limitation. Okay, that's the minimum. So we can't use minimum. We can't use minimum of that 24 phosphate. And we can't use the minimum of the 16 of the nitrogen. We should use more than that. And I was asking that which space is going to represent that more than that? Amanda, do you get it now?
Yes, sir.
And the space will be above that line, because remember, as you're moving from the origin out, the space is increasing. The numbers are increasing. So we need a number that is more than these limited lines. Okay? And that should be on the right side, not on the left side of the lines. Because the moment you come below the lines, you are moving towards 0. The moment you move out of the line, away from 0, you are increasing. And that is it. That is why we have this. So this section here, all right, this section here is the feasible, okay? This is the feasible solution area. That is the feasible solution area. And we know that our interest our interest is to get the vertices of this feasible solution area, okay? And please note, I just don't want it to be confused. The area really expands. It expands. The only thing is I've just tried to truncate it a bit, but it doesn't mean that there's a particular limit. It expands. I just decide to, because this is the limiting point on the x2 axis, 8, and this is a limiting point on the x1 axis, 8. I could decide to end them at this section there and that section there. It doesn't mean that it's part of a vertex. Okay. Now, Stephen, question is that, okay, so let's move on. Now we have the statement that we need the vertices. One of the vertices are this. Okay. This is the first vertex. Let me just let you know that. So the point here is one of the vertices. Okay. That point that you see here is one of the vertices. Okay. We call it vertex A. Let's call it A. This section here is another vertex. Let's call it vertex B. This section here is another vertex. Let's call it vertex C. That's all. We have only 3 vertices because it expands out and we don't know the rest. All right. So our feasible solution area is that space, but the feasible solution point is going to be either A, B, or C. A, B, or C. So we need the contents of A, B, and C. So let's go to A. If you go to A, you're going to substitute that into the objective function. Okay, substitute that into the objective function. Now, in case you've forgotten, the objective function says 6x1 plus 3x2. You're going to substitute that for x1 and x2. At A, what are the coordinates of x1 and x2? x1 is what? x2 is what? At A, what is x1 and what is x2? Eunice.
So please 0 and 8.
Good. So x1 is 0, x2 is 8. Okay. So let's get something here. So at point A, okay, we have 0 and then 8. Okay. So our z value will be 6x1, which is 0. Okay. 6x1, which is 0, plus 3x2, which is 8. And when you do that, you're going to get a value of what? 18, 24. You're going to get a value of 24. Now, why do you know that? Because obviously you can see that. Let me write it to you. We're going to get 24. Because 3 by 8 is 24, 6 by 0 is 0. So that is at point A. Now, at point B, we don't know yet because remember, that is 2 lines crossing. 2 lines crossing. So when you go to that section, that is 2 lines crossing here. So we will have to calculate simultaneously. We'll come to that. Let's go to point C. Okay. So at point C, we now find the value. And when you go to point C, the coordinates are 8 and 0. 8 and 0. Okay. So you now go and have your 8 and then 0 there. So the z value at point C is going to be 6 into bracket 8, okay, plus 3 into bracket 0. And that will give you 6 times 8. That will give you 6. You can tell me the value of that. 6 by 8, you can tell me the value of that.
32.
32?
No.
48.
48, thank you.
48.
Did you get it now? Okay, so that's 48. That's 48. Okay, 6 by 8. So now we have a value of 48, but we need that of B because we cannot go until we have the value of B. Okay, so how do we get B? Well, it's a simultaneous equation, so we've got to solve it simultaneously, okay, as we know. Remember, this is an equation that we have. Let me just take you back a little to the equation. okay, 2x1 plus 4x2, okay, we are going to make it equal to 16. And then 4x1, 3x2 equal to 24. Okay, so let's do that. You have 2x1 plus 4x2 equal to 16. Okay. And then the other one is 4x1 plus 3x2. 1 plus 3x2. Now, in terms of simultaneous equation, we can say that let's make it the equation 1. Let's call this equation 1, this equation 2. Okay, and let's make x1 the subject of equation 1. Okay, so you will have 2x1 equal to 16 minus 4x2. Divide both sides by 2, both sides by 2. x1 is equal to 8 minus 2x2. Okay, so that is your x1. Now drop this x1 back into 2. And so you have 4, instead of x1, you have into bracket 8 minus 2x2, close bracket, plus 3x2, okay, equal to 24. So that gives you 32 minus 8x2 plus 3x2 equal to 24. Okay, I'm just going systematic for reasons like that. Okay, so when you add this, you get minus 5. You take it to the right-hand side, you get plus 5x2. And then when you bring the 24 to here, you get 32 minus 24. That gives you what? That gives you 10. Is it 10? Okay. 24. Is it 6?
Give it 8.
That gives you 8.
That's done.
Okay. Yes. That gives you 8. Okay. So x2 is going to be 8 over 5. Now, sometimes if you are not really comfortable with some of this, just use decimals. 8 over 5 is 1.6. Let me see. Okay. 8 over 5.
Yes, sir, 1.6.
1.6.
And then that means we got to drop that into this value here, x1. So x1 is now equal to 8 minus 8 minus this will give you 4.8. Yeah? Yeah, I think it's going to be 4.8. Check. Okay, so x1 will be equal to 4.8. So eventually, your x1 will be 4.8 there. Okay, so let's write the z value. Z with the b is going to be 6 multiplying x1, which is 4.8, plus 3 multiplying x2, which is 1.6. So take your calculator. Okay. Take a calculator. You have 6 times 4.8. That gives you 28. Okay. 0.8. And then you have 3 times 1.6. 3 times 1.6. Okay. And when you check the answer, that is going to give you 36.3. 33.6. Okay. That is what I have. Final answer. Okay. Final answer is going to be 33.6. 33.6. So, some of these things, when you are working, you just work with me. So at this stage, we are going to now identify the optimal solution point. And remember, this is cost. This is cost. So the goal is to identify the lowest Z value, because Z is a cost. So if you look at 24, 33, 48, which coordinates gives us the lowest or the minimum cost? Which one? This one.
I have a 24.
Yes. This one, you don't have to go to Israel. Okay. You don't have to go to Israel at all to be able to come out with it. So let's go back to our coordinated vertices. So the point here, A, is going to give us the minimum. So you can see that it did not necessarily, occur at the intersection point, simultaneous equational intersection point. No, it's not all the time it can occur there. It occurred at one of the corner points. One of the corner points on the X and Y axis. And that is the final answer that we need to have. But once you've gotten this, you also have to substitute the values into the constraint to be sure that the constraints are also satisfied. Because remember, if you substitute it and one of the constraints is not binding or is not satisfied, then there's a problem. And we're going to try that pretty soon. Okay, so let's go back to the constraint. Okay. So the constraints are, if you can remember, okay, what was that? 2x1 plus 4x2. And we are told that it's supposed to be greater or equal to 16. So let's deal with the nitrogen constraint first. We're going to substitute our values that we have. And the values that we had for A, let's do for A first. Okay, the values we had for A was 0 and 8. Okay, the values for A. Okay, so we are doing for the values for A were 0. So you have 2 into bracket 0 plus 4 into bracket 8. Let's see whether it will be greater or equal to 16. When you look at it, is it greater or equal to 16? Absolutely. You get 32. Okay. So you get 32, which is truly greater than 16. Well satisfied. Okay. So A satisfies constraint nitrogen. Now let's see whether it satisfies constraint phosphate. Phosphate. Okay. I'm sure you remember that phosphate is 4x1 plus 6x2. 4x1 plus 3x2. So you have 4x1 plus 3x2. Okay. So that is 24. 3 by 8. The rest is 0. So that is 24. 24 is also greater than 16. This constraint is well satisfied. Now let's look at for B. For B, constraint 1. Okay. You have 2 into bracket x1 plus 4 into bracket x2. Okay. What is x1? Okay. Check your answers. Who can tell me? On mute. X1 is 4.8 and x2 is 1.6. So you have 4.8 and then 1.6. Okay. 4.8 and then 1.6. So I'll just take my calculator. 2 times 4.8 plus 4 times 1.6. You get 16 exactly. So you get 16, and that is satisfied and is equal to 16. So let's look at the second one. 4 into bracket 4.8 plus, what do you call it? 3 into bracket 1.6. Okay, I'm just substituting it into the equation.
Doc,
Yes?
And so I want to draw your attention to
Oh, I made a mistake.
Yes.
Okay, draw my attention. Let me see.
Yeah, so the second constraint for A, it should be 24 is equal to 24.
I wanted to be sure we're on the same page. So it's supposed to be 24, and this thing is not equal to, okay, it's supposed to be equal to 24, isn't it? Equal to 24. Okay. So that was satisfied for that. The second one, okay, so the second one is 4.8, blah, 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 blah. And that was 16. Okay, and the 16 is not greater than or equal to 24. You realize that? So the second one, the second constraint, the phosphate constraint is not satisfied. It is supposed to be 24 or more, but unfortunately, it is less than 24. So no wonder B did not give us optimum solution. But like I said, it's not always the case. Let's go to the last one, C, point C. At point C, you still will have the coordinates. What are the coordinates of point C? What are the coordinates of point C? Okay. C, you have what? 8 and 0. So you have 2 into bracket 8 plus 4 into bracket 0. And that gives us 16. And that is exactly equal to the 16 for the nitrogen. The second one is, yes, Janet.
I don't know if it is my calculation, but for point B, the 4 into brackets 4.8 plus 3 times 1.6 gave me 24, which is equal to the 24.
Oh, you had 24.
Mhm.
Oh, okay. Let's see. It is. Okay. Let's see. 4 times 4.8 plus 3 times 1.6. You're right. It gave you 24. Yeah, you're right. So 24. Okay, so that is not 16. Okay, thank you. That is not 16. That is 24, which is equal to 24. So that is also satisfied. Okay, at the edge. And then the last one, you have 4 into bracket 8 plus 3 into bracket 0. And that gives you 32. And 32 is greater than 24. So you can see that in all of these, all of them are binding. Okay, or let's put it, all of them are within the constraints. They are all within the constraint as expected. Okay, but one of them gave us a minimum, the minimum cost. Okay. Now, sometimes you be told, now what do these mean? Let's get something. Let's take a typical example of point B. Point B. Okay. What point B, the values are 16 and 24, they are at the edge, just like that of point A. They are also at the edge there, okay, 16 and 24. What it means is that the minimum requirement for nitrogen and phosphate were used, okay? The minimum requirement were used. They were used at the minimum, okay? And you don't want it to be below. But if you look at C, the minimum requirement for nitrogen was used. The exact minimum requirement for phosphate wasn't used, but it was still within. It was still in an acceptable, range of the feasible solution area. So that is how you attack these different kinds of questions. But the key point is knowing the optimal solution. Please note the optimal solution point was our value that we had for A, which was 0 and 8. So in order to minimize cost, In order to minimize costs, this organization, the board had to produce nothing for NPK. You should not produce NPK at all. You should just put all resources into the production of urea. And they should produce 8 bags of urea, which is the X2. Just show you this, 8 bags of urea, okay, which is X2 there. And don't produce anything of NPK. And if they should do that, they will incur the minimum, the lowest cost of 24 Ghana cedis. Okay. And that is how your advice is going to be. This is all of the pieces of advice. Okay. At this stage, I want to now go to how to convert the non-standard form equation. Okay. If you look on the left-hand side here, that is a non-standard form of the equation. We are going to convert this non-standard form into the standard form. Okay. It's just like the one we did for the Farmer Ghana Limited, but the only difference is that, remember that here we are minimizing cost. And so because we are minimizing, there's nothing called slacks. Remember we spoke about unused resources during the maximization. Now here, we are not going to talk about unused resources. It's not going to be the leftover resources. It's not going to be the fact that you were underutilizing resources, but this time you have gone beyond the minimum you were required to use. So we talk about surplus and not what? And not leftovers, or not wastages, or not slacks, but then we are going to talk about surpluses. So in a minimization, we talk about surplus. In a maximization, we talk about slacks. So what are surpluses? And remember, just like slacks, the surpluses are variables that are subtracted from the right-hand side constraint in order to convert it into the standard. Remember, in the slacks, we indicated that if you bring in the slack and you add the slacks to the constraint, if you add the slacks to the constraint in a maximization, you're going to now change the symbol into equal to. Now the opposite is here. If you add a surplus into the constraint in the minimization, this time you don't add it, but you have to subtract. You got to subtract the surplus from that, because the surplus becomes like excess above the minimum requirement. Okay. And so if you do that and then you subtract the excess, then you are now going to attach an equality sign. Of course, the surpluses are things that are extra surpluses. So it's just like in a maximization when you have underutilized resources, and so it's gone. It's gone. Their surplus is gone. It cannot be, retrieved again. And so they do not contribute anything to the objective function. This in the minimizing objective function, they don't contribute. And so the same way we will assign them a 0 value when we add them in the z function. Okay, we assign them a minimum value. So I'm going to write that, okay, and then we just establish the difference in the two of them. Just write and then establish the difference. So the first thing you're going to do is write the objective in the standard form. So this is the standard form. Standard form for this cost minimizing situation. So you will have z, min equal to, and then of course you know that we have our objective, which should come first. Okay, and the objective is 6x1 plus 3x2 plus our slacks, and we attach 0 to it. So 0s1. S1, sorry, our surplus. S1 will be the surplus for the nitrogen, and then 0s2 that will be the surplus for phosphate. Okay. They are 0. So it means that they don't contribute anything. Even if you multiply 0 by S1 and S2, you get back the same thing. They don't contribute anything. This is the standard form. Subject to, and then you write your nitrogen constraint. Like I've already indicated, you have to subtract the surplus from it. So the nitrogen constraint is 2x1 plus 4x2. You subtract the S1 from it and bring an equal to sign, and then bring your 16 pounds. And then you do for the phosphate as well. Okay, the phosphate is 4x1 plus 3x2. Subtract the S2 from it, the second surplus, and make it equal to the 24, which is for the phosphate. So now we've brought equality into this. Is the standard form. Okay. And then you write your non-negativity constraint, which must also include a surplus. So you have your x1, you have your x2, and then your surplus 1, and then your surplus 2, all greater than or equal to 0. This is how you convert the minimization into that situation of the standard. That's how you do the conversion. What a way! What a way to actually crack this code when it comes to this whole scenario. Your ability to be able to do this formulation is very powerful. Any question at this stage? Any question? Next time we meet, we are going to learn about the irregular types of linear programming problem. You see, all the linear programming problems we've looked at, they are regular. They are regular. They are not strange. But next time, we are going to look at 4 different kinds of strange linear programming. And then you'll be able to now master the basic. Okay? So we'll look at all of these 4 different kinds of linear programming next time, and you will be able to master the